Section 3.6, Zeros of Polynomial Functions. Let's begin. Evaluating a polynomial function using the remainder theorem. In the last section, we learned how to divide polynomials. We can now use the polynomial division to evaluate polynomials using the remainder theorem. If the polynomial is divided by x minus k, the remainder may be found quickly by evaluation of the polynomial function at k. So this k comes from, you always have x minus whatever 0 you have. So in the terms of x minus k, if I were to solve for x, I would get x equals k. So that's the number you're working with, you're evaluating with. Definition of the remainder theorem. If a polynomial f of x is divided by x minus k, then the remainder is the value f of k. So if I plug in your 0 or the number you're working with from the factor, then your remainder tells you is found by the last number. So if it's a 0, you should get a remainder of 0, just like in synthetic division. Let's go ahead and work this one out. Use the remainder theorem to evaluate f of x equals 6x to the 4th power minus x cubed minus 15x squared plus 2x minus 7 and x equals 2. All right, so let's go ahead and find f of 2. By doing so, we're left with 6 raised to 2 to the 4th power minus 2 cubed minus 15 squared, 15 times 2 squared, plus 2 times 2 minus 7. We're left with 6 times 2 to the 4th power. That gives us 16 minus 8 minus 15 times 8, 2 to the 2nd power. That gives us 4 plus 4 minus 7. 6 times 16, that gives us 96. So I have 96 minus 8 minus 16 plus 4 minus 7. If we add all that up, we get 25. So what does this mean? According to our remainder theorem, this right here is the remainder when dividing by x minus 2. Since we got x equals 2, that brings us to x minus 2. It's always x minus your c. Moving forward. Using the factor theorem to solve polynomial equations. The factor theorem is another theorem that helps us analyze polynomial equations. It tells us how zeros of polynomials are related to the factors. The factor theorem. According to the factor theorem, k is a zero of f of x if and only if f of k is a factor of f of x. Okay, well, this next example is asking us to show that x plus 2 is a factor of x cubed minus 6x squared minus x plus 6. Okay, well, we can use synthetic division. I have x plus 2, so this tells me I'm going to work with negative 2. Remember, you basically are just changing the sign. Okay, so if I perform synthetic division with negative 2, I go ahead and use the coefficients of each term. So that I have 1, negative 6, negative 1, and 30. I bring down my first number. Negative 2 times 1, we get negative 2. Negative 6 plus negative 2, negative 8. Negative 2 times negative 8, 16. Negative 1 plus 16 gives me 15. Negative 2 times 15 gives me negative 30. All right, so the first term, so that very first term is your remainder. And then you build up your polynomial. So it has no x, x squared. So really what we have is we've divided. We have x plus 2 as a factor. And this gives us x squared minus 8x plus 15. So if I were to multiply those polynomials, we would get that polynomial we started off with all over again. So if I were to multiply this, I would get this in return. So we kind of factored. Okay, well, it wants us to determine the remaining factors, find the remaining factors. To do so, we have to factor our trinomial. Well, hopefully that factors. Let's see. What numbers multiply to give me 15 and add to give me negative 8, negative 5, and negative 3? Okay, it does factor. So that factors to be x minus 5 and x minus 3. So what are all of our factors of our function? So this function right here is the same as all of these factors. We have x plus 2, x minus 5, and x minus 3. Using the rational zeros theorem to find rational zeros. The rational zeros theorem helps us narrow down the number of possible rational zeros using the rational of the functions, factors of the constant term, and the factors of the leading coefficient of the polynomial. Definition of rational zeros theorem. The rational zeros theorem states that a polynomial f of x has the integer coefficients. Then every zero f of x has the form of p over q, where p is the factor of the constant term, so that last number without an x, and q is the factor of the leading coefficient a sub n. When the leading coefficient is 1, the possible rational zeros are the factors of the constant term. So this is saying we need to make a fraction. This fraction is made up by the factors of the last number, this is your p, divided by the factors of your first number, that's your q. So I want factors of p divided by factors of q. Okay, so how many ways can I get 4 for my first one, p? I can get 4 from 1 times 4 and 2 times 2. So I get 1 times 4 and 2 times 2, right? So I can write 1, 2, and 4. Those are all the numbers that I can use to multiply together to get 4. But we need to keep in mind that it can also be, well, we want negative 4. So it can be negative 1 and positive 4, or it can be positive 1 and negative 4. We don't know the combination of it, right? So we always write plus or minus. And for our numerator, our leading coefficient, not numerator, our leading coefficient 2, I can get 2 from 1 times 2. So I write 1 and 2. But same thing, is it positive 1 and positive 2, or is it negative 1 and negative 2? So we also have to write plus or minus. So if it helps, you can disregard the sign and just always add plus or minus, because that's what's going to happen regardless. All right, now I need to create fractions using all these numbers. So I have 1 divided by 1, well that's just 1. And 1 divided by 2, that's just 2. And 4 divided by 1, that's just 4. Okay, so I used up my denominators of 1. What about my denominators of 2? So I have 1 divided by 2, that gives me 1/2. 2 divided by 2, that gives me 1. But I already have 1 over here, so I can just disregard it. And then I have 4 divided by 2, that gives me 2. Again, I already have 2 here, so I don't have to double count it. And those are all of your possible rational zeros. So my entire list would equal, so to answer this question, we would have plus or minus, and the collection of the numbers, so we use a curly bracket, 1, 2, 4, and 1/2. That's our answer. We have created a list of all possible rational zeros. Now, what does it mean to be, a little side note, what does it mean to be rational? A rational number is a number that's a fraction, a whole number, that's rational. Notice it doesn't include, it excludes irrational square roots, so like square root of 2. It excludes i's, which are complex. So if I have a zero that's one of these, it will not be found using a rational zero. So for these types of situations, you'll find these mostly with your quadratic formula. Find the zeros of polynomial functions. The rational zeros theorem helps us narrow down the list of possible rational zeros for the polynomial function. Once we have done this, we can use synthetic division repeatedly to determine all of the zeros of the polynomial function. Helpful steps to finding zeros of a polynomial function. Given a polynomial function f, we use synthetic division to find its zeros. So first we want to use the rational zeros theorem to list all possible rational zeros of the function. 2. Use synthetic division to evaluate a given possible zero by synthetically dividing the candidate into a polynomial. If the remainder is 0, which is your goal, the candidate is 0, the remainder is not 0, discard the candidate. 3. Repeat step 2 using the quotient found in synthetic division. If possible, continue until the quotient is a quadratic, so something squared. That's the goal. And 4, find the zeros of the quadratic function. 2 possible methods for solving quadratics are factoring using the quadratic formula. Okay, let's do the next problem. Find the zeros of 4x cubed minus 3x minus 1. Okay, so the problem here is if you start to think about it, it's not factorable. So how can we find the zeros if I can't factor? I also don't have a quadratic, so I can't use the quadratic formula. For such cases, we're left to use our list of possible rational zeros. So I want to find the factors of my last number, factors of q, which is 1, divided by factors of our leading coefficient, which is 4. So I can get 4 from, well, let's begin with 1. I can get 1 from 1 times 1, so it's just 1. For my denominator, I can get 4 from 1 times 4 and 2 times 2. So I have 1, 2, and 4. So my list of possible rational zeros are plus or minus 1 over 1 is 1. 1 divided by 2 is 1/2. And 1/4. So if I want to fully write down my list, I would have 1, negative 1, 1/2, and negative 1/2, 1/4, and negative 1/4. That's all of my rational zeros. Okay, now what do I have to do? I have to test them until I have, at the very least, a quadratic. Because once I have a quadratic, I can use quadratic formula and disregard this. If not, I repeat. Okay, so let's start off with 1. So we're just blindly testing the numbers. Your goal, so we're going to test these using synthetic division. With the goal of getting a 0. Okay, so let's start with 1. I'm going to perform synthetic division using 1 with our polynomial. So I have 4. There's no x squared, so I'll write 0, -3, and -1. Bring down the 4. 1 times 4 is 4. 0 plus 4 is 4. 1 times 4 is 4. -3 plus 4 is 1. 1 times 1 is 1. Cool. Super lucky. We got 0 on the first try. So what do we have? This right here, remember, we get no x, and then we keep going up a power. So we have 4x squared plus 4x plus 1. Okay? And then that 1 that I used to create synthetic division is also a factor that evenly divided our polynomial. So this gives us x minus 1. Okay, we have a quadratic. When you have a quadratic, you're kind of at that sweet spot where you're kind of done. Hopefully it factors. If it factors, you can go ahead and factor it. If not, you can use quadratic formula. But either way, you see the light at the end of the tunnel. You're almost done. All right, so can we factor? Let's see, what numbers? So my leading coefficient is not 1, so after the AC method. So 4 times 1 is 4. My middle term is 4. What numbers multiply to give you 4 and add to 4? 2 and 2. So this factors, I have to expand so that I have 4x squared plus 2x plus 2x plus 1. Group my first 2 and my last 2. I can factor a 2x, so I'm left with 2x plus 1. I can factor of 1, so I'm left with 2x plus 1. So this factors to be 2x plus 1 times 2x plus 1. All right, so that we have right now, we have x minus 1 and 2x plus 1 twice. You can write it squared if you want. There we go. We have fully factored. Now, what did our question want? We want to find the zeros. So last bit, we want to set each one equal to 0. I have x minus 1 equals 0, 2x plus 1 equals 0, and I don't have to write it twice. That one repeats. So plus 1, we get x is equal to 1, minus 1, 2x is equal to negative 1, divided by 2, x is equal to negative 1/2. And those are our zeros. Keep a note that this one has a multiplicity of 2 because it repeats twice. Using the fundamental theorem of algebra. The fundamental theorem of algebra states that if f of x is a polynomial of degree n greater than 0, then f of x has at least one complex 0. We can use this theorem to argue that if f of x is a polynomial of degree n greater than 1, and a is a non-zero real number, then f of x has exactly n linear factors. So we have that f of x is equal to a times x minus e1, x minus e2, all the way until you get your last 0, x minus en, where x1, x2, c1, c2, and cn are complex numbers. Therefore, f of x has nth roots if we allow for multiplicities. So one note I want to say is complex numbers includes your i's, but it also includes your real numbers. So it's just saying complex, your I, and also real. So what this is saying is your degree tells you how many zeros you will have. And that's including the fact that some zeros might repeat with multiplicities. Okay, so let's go ahead and do this example. Find the zeros of 3x cubed plus 9x squared plus x plus 3. I have a little hint there. List the possible rational zeros and use synthetic division so that you can find zeros. All right, let's start off by listing possible rational zeros. We want factors of 3, divided by factors of our leading number, which is also a 3. So I can get 3 from 1 times 3, and that's it. So my zeros are plus or minus 1 divided by 1 is 1, 3 divided by 1 is 3, 1/3, and 1 again. So that's it. So all of my zeros, or my possible rational zeros, are 1, -1, 3, -3, 1/3, and -1/3. Okay, let's go ahead and use synthetic division to find the zeros. So what we do is we kind of blindly test each one. Now for the sake of not making this video too long, the first one that works is -3. If you're doing these problems, I encourage you to look in the back of the book and see where to start off. So find 1 0 and start from there. So -3 works. This performs synthetic division with -3. The coefficients of our polynomial are 3, 9, 1, and 3. I bring down the 3 so that I have -3 times 3 gives me -9. 9 minus 9 is 0. -3 times 0 is 0. 1 plus 0 is 1. -3 times 1 is -3. I get a remainder of 0. So I have broke down my function. I have x plus 3. Notice I have a minus, but I wrote a plus. It's always opposite sign. And then here I have another factor, which is 3x squared plus 0x, so no x, plus 1. Okay, so now we're left to solve for this one right here. To solve for that one, I can go ahead and use the square root property. So I can set it equal to 0. I have 3x squared plus 1 is equal to 0, minus 1 minus 1. 3x squared is equal to -1, divided by 3, divided by 3. X squared is equal to -1/3. Take the square root, don't forget plus or minus. So I have x is equal to plus or minus the square root of 1/3, -1/3. So this gives us plus or minus, or plus the square root of 1/3 and the negative square root of 1/3. All right, always rationalize. So the square root applies to the top and the bottom. We always avoid having radicals in the bottom, so you rationalize. So you multiply by the square root to the top and bottom. So you're left with the square root of 1 is 1, so 1 square root of 3. So just square root of 3 over 3, and square root of 3 over 3. Those are our two zeros. So your answer is x is equal to, well, we have -3 from our first one, and then we have square root of 3 over 3 and negative square root of 3 over 3. Using the linear factorization theorem to find polynomials with given zeros. This means we can factor the polynomial functions into n factors. The linear factorization theorem tells us that a polynomial function will have the same number of factors as its degree. Super important. And that each factor will be of the form of x minus c, where c is a complex number. This means both real and complex numbers. Definition of complex conjugate theorem. Complex conjugate theorem. According to the linear factorization theorem, a polynomial function will have the same number of factors as its degree. and each factor will be in the form of x minus c, where c is a complex number. If the polynomial function f has real coefficients and complex zero in the form of a plus bi, then the complex conjugate of a zero, a minus bi, is also a zero. So one thing I want to point out that I don't think gets enough attention is the fact that it can trick you. If you're given a problem and you're asked to find the polynomial, it can trick you and only give you one of the complex answers. From there, we're supposed to catch on and say, hey, if I have one complex answer, I also have the conjugate. Okay, so let's do this example. Find the fourth degree polynomial with real coefficients that has zeros of -3, 2, and I, such that f of 2, -2 equals 100. So fourth degree polynomial, this means I have to have 4 zeros. So I have x minus my first zero, x minus my second zero, x minus my third zero, and x minus my fourth zero. But here it tells me my zeros are only 3 of them, -3, 2, and I. So I need to catch on and say, hey, I also have -I. So that I is the same as 0 plus I. So the conjugate would be 0 minus I, which is just -I. Okay, so let's first start off by writing all of our zeros as factors. So I have x minus -3, x minus 2, x minus I, and x minus -I. Notice I always write x minus. Let's clean this up. So I have x plus 3, x minus 2, x minus I, and x plus I. Okay, now it's also giving me this extra information that I'm not too sure how to use. So I have f of -2 equals 100. When it gives you that, this is telling you that we have a coefficient to consider. So if you recall, our function is actually f of x is equal to a times x plus 3, x minus 2, x minus I, and x plus I. And I can find a by using the fact that f of -2 is equal to 100. So let's plug in an x of -2 and let's set it equal to 100. So that we have 100 is equal to a times, and for each one of these, for x, I'm going to write -2. So that I have -2 plus 3, -2 minus 2, -2 minus I, and -2 plus I. That's going to help me find a of my function. Okay, let's clean our values up a bit. So I have 100 equals a times -2 plus 3 is 1. -2 minus 2, that gives us -4. -2i minus I can't clean that up any further. And -2 plus I. Okay, I have to start off by multiplying our i's. Let's go ahead and FOIL. So I have -2 times -2 is 4. -2 times I is -2i. -I times -2 plus I plus 2i. And -I times I, that gives us -I squared. Right? And I squared is -1 times a negative. So you can FOIL, or you can use your little trick. It's difference of squares, so it's always your first term, so -2 squared minus your second term. 1 squared. So that we get 4 minus, that was I squared, which is negative 1, which just gives us 4 plus 1, we get 5. Okay, so next is going to be Descartes' rule of signs, but you can read that on your own. You can skip it completely. It's more effort than what it's worth. So I was just going to say, look at that if you'd like. Let's go back to this problem. So far we have 100 is equal to a times 1 times negative 4 times 5. All right, well, negative 4 times 5 is negative 20. Times 1 is just still negative 20. So I have negative 20a is equal to 100 divided by negative 20 divided by negative 20. A is equal to negative 1/5. So our final answer, our fourth degree polynomial, would be f of x is equal to negative 1/5 times x plus 3, x minus 2, x minus I, and x plus I. That is our answer. If you like to, you can go ahead and multiply all of these values out. Oh, I'm sorry. I totally made a mistake right here. 100 divided by negative 20 is negative 5. So that's supposed to be negative 5. Totally got ahead of myself. If you like to, you can go ahead and multiply all of this out. So then you get negative 5x to the fourth minus 5x cubed plus 25x squared minus 5x plus 30. This is a really lengthy problem, but it's so cool. It kind of ties up everything we've learned and puts it all together. Your homework for this section was 7 through 45, every other odd, 57, 59, 67, and 69. That was 3.6 zeros of polynomials, of polynomial functions. Thanks.